Hi everybody, this is our sixth segment of the Cenozoic chapter, and this last one, it's going to be the last one, is about the Quaternary. The Quaternary is important because this is when the glaciation have happened, which is kind of important for us, especially because this is defining our evolution also. So I will ask this on the finals. You better know it. What do we need to onset an ice age? The first and most important is that we have to have a continent at the pole. Because if we don't have continent at the pole, what do we have? Yes, we have the seawater. What do we know about the seawater? That it's salty. And when you have the salty seawater and the ice, the snow falling on it, then what's going to happen? Yes, it's gonna melt, and you're ending up with no snow. And the color of the ocean is relatively like grayish, bluish. So therefore, some of the sun heat gets absorbed by it and just partially will refract back into the atmosphere. On the other hand, when you have land at the pole, then the snow falls on it, and when the sun hits the snow, it will refract completely back because the albedo is much higher when you have white snow on the land versus when you don't. So the other thing which you need for the ice age is to have to learn about the oceanic circulation. And when you have like an ice age is getting set up, usually there will be a current developing around the continent at the pole, and that's going to be a cold current which actually completely shuts down any warm current touching the cold area. So therefore we call it icebox effect, because no any warm water can get to the continents at the pole. So therefore it really sets it up for the ice age. So remember, continent at the pole, albedo, and the icebox effect. These are the things you have to know. So it's not enough just to say that there has to be a continent at the pole. It's not going to be enough. So first of all, we have to talk about the ice age. You have to understand that when we have an ice age, it's not just going to be cold all the time. We actually, during the ice age, we have the so-called glacial, interglacial cyclicity. So I'm going to compare what do we have during the glacial times versus during the interglacial times. So during the glacial times, we have the continental glaciers, which are advancing toward the equator. We have alpine glaciers, which are advancing downslope. The sea level is going down, which means eusteric regression, which means the sea level is going down. The reason for that is because the water is being trapped in the glaciers and also in the continental glaciers. The sea level can go down more than 100 meters actually. In response, the rivers have to cut down because the sea level is going down, so the rivers have to cut down also. So they will actually cut into their own terraces, which means sediment, which was deposited by them before. In this case, the land surface is depressed under up to 3 kilometer ice. So remember, the ice, the thickness of the ice could be 1.6, 1.7 miles thick. And of course, when the cold climate is coming in, the animals have to migrate into warmer areas. On the other hand, during interglacials, we got retreating glaciers. We have, because of the glaciers melt, the continent is actually rebounding, from the pressure of the ice. It's actually kind of going up. The sea level is going to rise. It could be maximum 30 meters higher, which means 90 feet higher than it is today. And the coastal river valley is like just as Chesapeake Bay is actually will flood, and it forms estuaries. Estuaries, when when the water is not fresh and not really salty. It's in between, it's brackish. And then, of course, the animals and plants are migrating the other way. This figure is actually animated, so when you play the slideshow, you can see that during interglacial, the sea level goes up, and during glacial, it's actually going down. Now, what causes all this cyclicity? Why do we have glacial, interglacial periods? Nobody knew it until the beginning of the 19th, 20th century, where a Serbian mathematician, Milutin Milankovitch, who was a mathematician, I might have said it already, and he actually, what he realized is that the cycles must be influenced by the gravitational forces in the solar system. We all know that the moon has a major influence on our climate, because not the climate, but the tides, you know. And so you have to imagine that the moon is a relatively small object, and every other planet is actually much bigger. So they have to have influence on our orbital parameters as well. So that's what he calculated. And what he came up with is that there are actually 3 periodic cycles in our orbital parameters. So we're going to go through those now one by one. The first one, before I get into the eccentricity, sorry, I didn't remember that I had this slide here. The calculations he come up with, and the explanation he come up with, is what we call Milankovitch Theory. I want you to know this because it's kind of important. The Milankovitch Theory actually explains that as the Earth travels through space around the Sun, the 3 elements of the Earth-Sun geometry produce variations in the amount of solar energy that reaches the Earth. So this is what we call Milankovitch Theory. Okay, so the 3 changes, the first one is the eccentricity. The eccentricity describes the shape of the Earth orbit around the Sun. You all know that right now it's an ellipsoid. Of course, it's not much of an ellipsoid. It's only by 5%, so it's really not that much. There are times when it's like 5% ellipsoid, and there are times when it's absolutely a circle. So it goes from ellipsoid to a circle. The cycle of this is 100,000 years. And you understand that, that it does change the amount of solar radiation the Earth gets during the year. Right now, the current eccentricity is less than 0.02%, and it, as I just told you, it varies between 0 to 5%. So right now we are almost close to circle. The next parameter is the obliquity, and the obliquity describes the tilt of the Earth axis. So the Earth axis, I have to do it this way because this way is how the Earth axis is. So the Earth axis has a tilt, and this obliquity is responsible for the 4th season we have. Currently, the Earth axis is tilted about 23.4 degrees. The degree of the tilt through the Earth history has been varied between 21 to 24.5. And the cycle from the 21.5 to the 24.5 takes about 41,000 years to occur. So that's obliquity, and that is the axis of the Earth. It changes between 21.5 and 24.5. And remember, right now it's 23.4. When the northern hemisphere is tilted 23.4 degrees toward the sun, there is summer there, while the southern hemisphere is experiencing a winter. And the opposite is expected when the northern hemisphere is tilted about 23.4 degrees away from the sun. During the summer in the northern hemisphere, there are more hours of sunlight, which allows more long-wave radiation to reach Earth. So it's kind of making a difference. It's very, very important. And this slide is just showing you the tilt. And the last one, and probably the most important in my brain, because this is the signal we see most in the rocks. the precession. And the precession describes the change in orientation of the Earth's rotational axis in respect to the stars and the sun. And the degree in which the axis is tilted doesn't change because of the precession. This is also known as the precession of the equinoxes because the orientation of the Earth rotational axis is changing. The time of year or season typically occur changes. So you have to imagine that Earth is wobbling around the precession, around the obliquity. So through time, actually, there are times when it points toward the sun, and there are times when it points away from the sun. So it's kind of important. So you have to imagine the precession of the axis as like a spin, a spinning top. So the precession has a cycle of 20,000 years right here. And as I said, there are times when Earth is pointing toward the sun, and other times it points away from the sun. So in approximately 11,000 years, the northern hemisphere will experience summer when the Earth is closest to the sun. Summer will occur in December and winter will occur in July, when it's going to be like that. Now you have to imagine that these 3 cycles actually on top of each other. So you're going to get a very complicated signal which is influenced by all these 3. So let's say this is eccentricity right here, 100,000 year cycle. And there is obliquity, 41,000 years. And then there is precession on top of that with 20,000 years. So you have to imagine that these 3 cycles really influence each other a whole lot. So you have to imagine that continuous changes of these parameters cause the amount of solar heat received at any latitude to vary slightly over time. Milankovitch proposed that the interaction of these parameters provides the triggering mechanism for the glacial, interglacial cycles of the Quaternary. And I really truly believe that he was right. If you think about it, it's not only in the Quaternary, it's actually, when you go back in time, you can see these cycles, and actually the duration of the cycles are always the same, all the way from, as the best I know, like I have had fellow graduate students working on Proterozoic in Canada, and it had beautiful carbonate cycles with the duration of about 20,000 years. I had my professor and other fellow grad students working on the Cambrian in Virginia. And then I was working on Triassic. We have these cycles all through the Earth history. And probably the strongest signal is the 20,000 years, but you can clearly see the 100,000 and actually the obliquity also. And this slide really clearly shows you the 3 signal, the eccentricity, obliquity, and the precession, and the synthetic summary curve, and this is the oxygen isotope curve. It's pretty amazing how much the oxygen isotope curve actually correlates with the synthetic sum curve, like the summary of the 3, I should say. So after this, we can jump into the Quaternary. I'm thinking that I should get another segment, actually. Even though I thought this was it, I can put another one. So I'll see you in the very last segment.